Topic 2.2 Electron configuration. Electromagnetic radiation is the radiant energy released by certain electromagnetic process. Electromagnetic radiation is also characterized by its wavelengths and frequency. The energy of the electromagnetic radiation is inversely proportional to the wavelengths. The wavelength is related to the frequency of the radiation by the expression, where c is equal to the speed of the light. In IB chemistry, this equation is more useful than the other one. And also, I strongly suggest you to remember this relationship. Electromagnetic spectrum, EMS, is a spectrum of wavelengths that comprise the various types of the electromagnetic radiation. You need to know the order of the wavelengths in this spectrum. However, you don't need to memorize the numbers, but you need to know the order of the things and the trend. Means you have to know that as you go from the radio to gamma ray, the frequency increases, the length of the wavelengths decreasing, and the quantum energy increases. Okay, so remember that when you have a low frequency, it has long wavelengths and it has low quantum energy. When you have a high frequency, it has short wavelengths and high quantum energy. So let's talk about the electromagnetic spectrum. So we need to learn 3 different types of the spectrum in this topic, and this spectrum origins from any of incandescent solid, liquid, or compressed gas, and we call this black body. And then they are hot, okay, hot black body. So when we create the spectrum directly from this hot black body, we create a continuous spectrum, okay, and the emission spectrum and absorption spectrum can be created by passing through gas cloud. Okay, so when this light goes through the gas cloud, we create the emission spectrum and absorption spectrum. Okay, and emission and absorption spectra are the characteristic of the chemical composition of the cloud. Okay, so let's summarize this, okay? So continuous spectrum happens when it is emitted by the hot solid, so mean directly from the hot black body. And the line spectra is emitted by the hot monoatomic gases. So the emission spectra or the line spectra is happening when it is emitted by hot monoatomic gases. Okay, so still goes through the gas cloud, but is emitted by the hot monoatomic gases. And continuous, we just talked about the continuous spectrum, right? So let's talk about the absorption spectrum. Absorption spectra formed by the light passing through a cooler vapor. Okay, so it is formed of the light passing through a cooler paper. Okay, and the paper observes those regions of the spectrum which it would have emitted and had it been in an excited state. Okay. So once again, continuous spectra, also called a thermal or blackbody spectra, are emitted by any object that radiates heat and has a temperature. The light is spread out into the continuous band with every wavelength having some amount of the radiation. So for example, when sunlight is passed through a prism, its light is spread out into its colors. An emission spectrum or emission spectra occurs when the atom and molecules in a hot gas emit extra light at a certain wavelength, causing bright lines to appear in a spectra. As with the observation spectra, the pattern of these lines are unique for each element, and we can see emission spectra from comets, nebula, and certain types of the stars. And observation spectra, if you look closely at the sun spectrum, you will notice the presence of the dark lines. These lines are caused by the sun's atmosphere observing the light at a certain wavelengths, causing the intensity of the light at these wavelengths to drop and appear dark. The atom and molecules in a gas we observe only certain wavelengths of the light, and the pattern of these lines is unique to each element and tells us what elements make up the atmosphere of the sun, and we usually see this observation spectra from the regions in space where a cooler gas lies between us and a hotter source. And we usually see observation spectrum from stars, planets with the atmosphere, and galaxies. Okay, so let's talk about the Bohr's theory of the hydrogen atom. Bohr's model of the hydrogen is based on the non-classical assumption that electrons travel in specific cells or orbitals around the nucleus. The Bohr's theory of the hydrogen atom. Bohr's model of the hydrogen is based on the non-classical assumption that electrons travel in specific shells or orbitals around the nucleus. Bohr explained the hydrogen spectrum in terms of electrons observing and emitting photons to change energy levels. And Bohr's model does not work for systems with more than one electron. So we can literally have only explain this theory using the hydrogen atom. Okay. So let's talk about the emission spectra a little bit further. Electrons can only exist in certain fixed energy levels, and these levels related to the amount of the energy an electron has. Okay. So in this class, we know that energy level 1 can hold up to 2 electrons, right? And energy level 2 can hold up to 8 electrons. Energy level 3 can hold up to 18 electrons, and so on. Okay, so let's talk about the atomic states. Okay, so we can have two different types of state. First one is called ground state, and next one is called excited state. Okay, so when an atom has the lowest amount of energy, we say the atom is at the ground state. And when an atom has excess energy, we say the atom is in excited states. Okay, so an atom without energy begins at the ground state. So all the atoms that we know, okay, the original state is actually called the ground state. Okay. And when atom observes energy from an outside source, it enters an excited state. And when an atom emits the photon of the light, it returns back to its ground state. So let's look at this diagram together. Okay, so we have hydrogen atom, right? And hydrogen atom is at the ground state. So means it's like at the original states, okay? And when it receives the energy, some hydrogen atoms becomes excited, okay? Means they absorb the energy and they have more energy than they needed. So when that happens, they're going to emit photons of the light, okay? So they can go back to the its ground state. And when that happens, it's coming back to the ground state. Okay, so we now know what is meant by the ground states and excited states, right? Then let's apply this concept to the line spectrum. Okay, so when the light emitted by an element, its electrons return to a lower energy state, and it can be viewed as a bright line emission spectrum, right? So when the light emitted by the electrons and electrons are returning, when electrons return to the different energy levels, it is going to show up in different part of the spectrum. Okay, so when electrons return to energy level 1, it's going to show up in UV. And when electrons are returned to the energy level 2, it's going to show up in visible part of the spectrum. And when electrons are returned to energy level 3, it's going to show up in IR part of the spectrum. Okay, and depends on the energy level they are returning to, they are actually named differently. So when the electrons return to energy level 1, we call these electrons Riemann series, and when electrons return to energy level 2, we call it Balmer series, and when electrons return to energy level 3, we call it Paschen series, and when electrons are returning to energy level 4, we call it bracket series.